This is the embedded systems design class. Last time we talked about the uh, power saving modes. We talked about the reset module. And the end of that talk, I said that we will move to discuss the external memory and how to interface it, how to program it. However, I think we are ready to discuss the interrupts first. Once we're done, we will move to the external memory. In this talk, we will check the polling technique versus the interrupt-driven technique. We will go through the interrupt service routine, how to code them, how to make sure they are written in an efficient way. We will check also the vector table, the priority, and the interrupt service routine overhead, among many other subjects. So let's start by defining the build I/O and the interrupt-driven I/O and see the difference between them. In the build I/O, the processor continually checks if the I/O device is ready for the data transfer. It do this over and over again. It consumes a lot of time from the CPU, and that's why it's inefficient. The time is always wasted checking for ready conditions. As you can see here, now the CPU initiates the checking, checks if the I/O is ready. The I/O respond yes or no. And again, let's say the I/O is not ready. The CPU check again. The I/O is not ready. The CPU again checks once more, and then the I/O may be not ready, and keeps doing this until the I/O ready for the CPU. Now, we know that the CPU usually runs on a higher frequency compared to the I/O. So you have two scenarios here. Either you check, either the CPU is going to check too often or not often enough. To give you an example that is from the real world, let's say you are in a lecture room and you are giving a talk, and you know that somebody will come to the room to give you a certain document. So in the build I/O, what you're going to do, the door is closed. Every once in a while, you go open the door and check if he's coming or not. And then again, you do the same. Again, you do the same. You always stop talking, stop the lecture, stop what you're doing, which is usually important. And then you go check the door and come back. Obviously, this is not efficient. The efficient way is the interrupt-driven I/O. Now, to see also the too often and not often enough checking, in the example, if you, let's say that it happens that this guy that will deliver the document for you, he will come after 10 minutes. If you check every second, or every second is too much, I think. So let's say that if you check every 30 seconds, so every half a minute, you stop the talk, you go check the door. Again, you stop the talk and check the door. So that's too much checking. It's too often. You probably will check 20 times before you find him. Or maybe you're not, or you are not checking enough. So if the guy, let's say he comes after 10 minutes and you are checking only after 20 minutes. So the CPU will, the guy will come at the door. He cannot do anything. He'll just wait for you to open the door, and he will wait and keep waiting for 10 more minutes until you go and check out. So, and bottom line here, this is not efficient. The efficient way is the interrupt-driven I/O. Now the I/O device interrupts the processor in the interrupt-driven I/O. When you use interrupts, the I/O can initiate the exchange and interrupt the processor when it is ready for data transfer on any job. This is very efficient, so the processor doesn't have to worry about anything. It keeps executing. Once the I/O is done, it will get or give the CPU an interrupt. So the CPU can, after a while or directly, can service this interrupt. Now, modern computers, modern microcontrollers, they all use interrupt-driven I/O. Now, to understand how the interrupt operation happen, in software, this what will happen in a normal program flow. You will have main function, you execute the first instruction, second instruction, third instruction, and so on. Let's say that you reach to instruction N, an interrupt happened to you. If the interrupt occur, now the main method will stop executing this instruction, and notice that the interrupt could happen right after the instruction start executing, maybe somewhere here, or somewhere in the middle, or at the end of the instruction. At any way, the program will continue finishing this, executing this instruction. At the end, it will start the interrupt procedure. So what happens is, first, the status or the lower byte, the CPU priority level, and the return address will be pushed to a stack. The CPU priority level will set to the priority of the pending interrupt. So if the main has a certain interrupt priority, the interrupt service routine, which will serve or handle the interrupt, will have a higher priority. So it will be executed, and once you're done, you will come back to the normal program flow, but it needs to do certain things. As you can see here, store everything related to the main method. So what is the status? What is the priority level? And also the return address. So when you're done, you return to the next instruction, which is instruction N+1. Also, the CPU priority level is set to the priority of this interrupt service routine. And then the BC sets to the interrupt vector pointing to the address of the ISR. It has this type, usually underscore ISR, sometimes underscore ISR fast. And then it has a certain name based on the event that happens or the interrupt that occurs. Inside the interrupt service routine, there are things that you need, the interrupt service routine is responsible for. It saves the context, it serves the interrupt, and it restores the context again before returning back. Now, to return back, you will do the same thing that you've done before. The status lower byte, the CPU priority level, and the return address will be popped from the stack. The CPU priority level will be set to priority of the main method, and then the BC will jump to the next address here and continue working. Now, there are things here that you need to make sure of. The first one is the normal program flow. The normal program flow, which is the main, is referred to as the foreground code. The interrupt service routine, or the ISR, is referred to as the background code. Now, if you look at the main method, you will not see any call for the ISR. So there is no calls. Actually, there should be an event. This event happen and interrupt the normal execution of the main method. This is a common mistake between the students when they deal with interrupt service routine. They always look for a call for the interrupt service routine that is never shown in the code. It happens only when a certain event happens, and we will have many examples of the types of the interrupts. Okay. Now, to know exactly where does this interrupt service routine and to know its address, we need a vector table that contains the starting address of different or several ISRs for each interrupt source. As you can see here, you have from the beginning of the uh, program memory, which is 0x0000, you have the goto instruction and the goto address, and there are certain things that reserved for the big 24. After that, you have these 5 interrupt vectors. They are specialized interrupt vectors that are called trap vectors. One of them is the oscillator fail. When the oscillator fail, that's a very high interrupt priority that you need to work on immediately. Also, following that, the address error, following that, the stack error, the math error, and the DMAC error. Notice that they are very critical here. This is why they have a higher priority. Now, if you see here on the side, we say that this is the decreasing natural order priority. This is called a natural priority. So this will be the highest one, followed by the next one, followed by the next one, and so on. So if 2 events, let's say the oscillator fail happens and the DMAC error also happen. If these 2 events happen, we serve the oscillator fail first. Now you also have the some reserved locations, and then starting from this position, you have interrupt vector 0, interrupt vector 1, all the way to 117. Now, in case of our big 24, our microcontroller, we will define its interrupt service routine right there. Actually, Microchip company already defined that for us, but this is actually is in a general sense. Now, this part here from this address all the way to this address is called the interrupt vector table, or the EVT. We repeat the same thing again here for an alternate interrupt vector table. This is for reliability, because these addresses are very critical for the microcontroller to work fine. And as we discussed before, we will start our code at this location, which is 200 in hexadecimal. All right, so let's see what we can put here. So we have these failures or trap ISRs that, or the trap addresses that we need to put first: the oscillator, the address error, the stack error, and the math error. Following this, we have vectors that weren't defined in the general sense. Now in the big 24, they are actually defined for each one of our needs. So one of them is interrupt 0. This is an external interrupt that I can't define anything for it. We have the input capture, even though we didn't discuss that. We have the output compare. We have the timer. We have timer 1, 2, and 3. And we have other things that we will study today, like the interrupt 0. We have interrupt 1. We have the change notification interrupts. We have also many others that we will discuss later in future lectures, like the communication interrupt for sending and receiving, for SPI and UART, and many other things. Also, we have interrupts for the analog to digital converter, and that's the change notification interrupt that we will talk about today. If you see for the external interrupt, we have interrupt 0, we have interrupt 1, and we have interrupt 2. So in a natural priority level, interrupt 0 will be executed first, followed by interrupt 1 and interrupt 2 if there are only the 3 interrupts that you defined in your code. As you can see here, we just take 2 examples. We say that this is the serial data or the SPI interrupt. This is the serial peripheral interface. And the SPI1 interrupt, it means that the transfer is done. This is what does it mean. Once the transfer is done, it will initiate this interrupt that you need to handle. Similarly, here we have the change notification interrupt. So whenever you have a change in one of the pins, where the value was 0 and then it jumped to 1, or it was 1 and then it jumps back to 0, there is a change in the value, it will generate this interrupt. And now you can see that there are so many events. Like for the timer, whenever the timer is expired, it will generate an interrupt. And we mentioned that there is an interrupt flag for the timer that we need to worry about when we program. Now, the same thing happens if you use an interrupt-driven technique. And so these are so many examples. It's very important when you write down any interrupt service routine that you know its name. Of course, this table will be given to you. You don't have to memorize it, but you need to look it up and make sure that it is the correct name. Now, the natural priority versus, or the difference between the natural priority and the assigned priority. You can assign also priority. That's something different than the natural priority. The normal instruction execution has priority of 0. Any interrupt service routine, you can assign a priority for it, and you have the 8 options from 0 to 7. Now, for the assigned priorities, an interrupt service routine, priority must be more than 0 to make the interrupt execute, or to make sure that the interrupt execute. It cannot be 0, it's because this is the main method priority. So if you assign a 0 for it, actually it is already assigned. So if you put an interrupt service routine and you write the code for it and you were doing everything for it, but you assigned a 0 to it, once the interrupt happens, it will compare the assigned priority first, and it will see that it is 0 and the normal priority also 0. So they are at the same level. It's not higher than the normal execution, and the interrupt won't happen. So you must assign a priority of higher than 0. If you assign a priority of 0 to an ISR, it's like you are disabling the ISR. So an ISR1 with a higher assigned priority can interrupt a currently executing interrupt service routine 2 with a lower assigned priority. So if we make ISR priority 3 and ISR 2 6, if ISR1 priority is, let's say, 5, let me write it down. That's the assigned priority for ISR1. And for ISR2, if the priority is 3, now ISR2 assigned priority is lower, which means that I will execute ISR1 first, followed by ISR2. Now, if a simultaneous ISR occurs at the same cycle, and they both have the same assigned priority, in this example, let's say both of them were 5. What will happen then? The interrupt with the lower natural priority, or lower vector number, or its address is lower, will be executed first. And that's an example. If you have interrupt 0 and interrupt 1, and you assign both of them the assigned priority 5, then you will go back to this table and you will notice that interrupt 0 compared to interrupt 1. Interrupt 0 is having a lower address, which means it will execute before interrupt 1. Remember, we said that at this direction, with this arrow, we have a decreasing natural priority. So now we see the relation. When an interrupt service routine is at the starting point of being handled, you check the assigned priority first and then the natural priority if the assigned priority are equal. Now, with every interrupt, you have to enable this interrupt. So each interrupt source has certain bits that can help you with that. It has 3 bits. They are always very critical. Even when you write your code, you will define them one by one. You will see their statement is sequential. So you have a flag bit, you have a priority bit, and you have an enable bit. The flag bit is only a single bit. You set the flag, or the flag will be equal to 1 whenever the flag condition is true, or whenever the event happen, this flag value will be equal to 1. The interrupt service routine, and that's very critical. Inside the interrupt service routine body, you must clear the flag bit. So the flag bit is giving an indication that this event happened. Once you go inside the interrupt service routine, you need to reset this flag. And we've done this with the timer, if you remember. If not, if you didn't do this step inside the interrupt service routine, then you will get stuck in an infinite loop and you cannot make advantage or make use of your system. Now for the priority bits, since you have priorities from 0 all the way to 7, then you need 3 bits to distinguish between the assigned priorities. So the priority bits sets the interrupt priority, obviously. And we talked about this in the previous slide. The enable bit must be 1, and the interrupt priority must be larger than 0. So both of these conditions must be true for the ISR to be executed. So you must enable it by assigning this bit to 1, and the priority bit must be larger than 0 for the ISR to be executed. Now the enable bit does not have to be 1 for the flag bits to be set. So be aware of this. Sometimes when you disable the interrupt, you don't worry about the flag anymore, and it could cause troubles for you. So make sure of this point. Now, by default, the interrupt ISR are disabled from execution, which means all the priority bits and enable bits are equal to 0 by default. Now, what about the critical traps? So we differentiate between traps and interrupts. A trap is a special type of interrupt. It is non-maskable, and it has a higher priority than any other interrupts, or what we call normal interrupts. Traps are always enabled. You cannot disable them. So these traps, they don't follow what we said here by default. We have 2 types, the hard trap and the soft trap. The hard trap, the CPU stops after the instruction at which the trap occurs. It cannot continue. It's like a very problematic event. For the soft trap, the CPU continues executing instruction as the trap is sampled and acknowledged, and sometimes you can recover from it. And you can see the type of traps. There are 5 of them, as you can see here. We have the oscillator failure and the address error. They both are hard. Their priority, as you can see here, is very high. And they have their flags associated with each one of them. We have the oscillator fail, or the CF, the clock fail. And these are the bit fields. And where do you find them, in which special function register status fields. The address error, we have the address error, which is in this condition special function register, the interrupt condition or control register. And we have the stack error, math error, and the DMAC error with their name and fields, as you can see here. They are soft errors and they have lower priority. So this is for the traps. Usually when you buy a new microcontroller and you code in an efficient way, you won't face these troubles. So let's say you work with the other interrupts, the normal interrupts. To work with them nicely, you need to understand how the PIC24 deal with interrupts, starting with the interrupt latency. So you need to know exactly what happens when you enter or move from the main method, let's say, to the interrupt service routine. So what happens in the entry and what happens also in the exit. And this timing diagram, we check the PC, the program counter, and between the parentheses, we just label the routine, whether it's the main or the interrupt service routine. Also here we have instructions, the follow of the execution of the instruction, what's going on, and also the interrupt priority. So in the green part here, we are working in the main, and the priority is, let's say, we assume that it is equal to 4. So we assigned 4 for the main. As you can see, this is the TCY here. So let's say that you executed instruction A, and while you are executing instruction A, somewhere in there, an interrupt event occurs. So what happens now automatically, since you are doing pipelining in the microcontroller processor, you will fetch the next instruction, which is the instruction P. You will waste a cycle there, and you know that an interrupt really happened. So you start moving from the main to the interrupt service routine. You must have a no operation. During this no operation or this knob, you save the BC of the instruction B. So when you return back, when you exit, you know exactly where to continue from. And then you need another cycle to go to the vector table and fetch the address of the interrupt service routine. At that point, you push the BC low 16 bits, followed by pushing the BC high 8 bits along with the status register. So at this point here, you officially entered the interrupt service routine. Let's say that this interrupt service routine at this address, which is 2000. And now, after that, you will start executing the interrupt service routine first instruction, which is instruction 1, 2, 3, and so on. So if you look at this here, you see in this box that you needed actually 4 cycles for the interrupt service routine entry. as you can see, 3 of them is considered to be with the main and 1 of them inside the interrupt service routine body, but it doesn't matter to us. In terms of latency, we need 4 cycles from the interrupt occurrence until we started execution the first instruction. Now, the ISR will handle the interrupt, whatever is the type of the interrupt. Once you're about to exit, the last statement or instruction in the body of the ISR is the return instruction. So let's say that you continue executing the ISR and you reach to 2000 plus X, where X is actually more than 2006, obviously. So let's say that was the last instruction of the ISR. And after that, you call the return. Now, the return is a special function, or sorry, it's a special instruction where it needs 2 cycles. If you look at the table in the data sheet of the BIC24, you will see that the return instruction is or needs 2 cycles. And after that, you need also a no operation, which is part of the main method now. So in these instructions, in the return, because it needs 2 cycles and also an up, actually what happens here is you need to do the opposite of what we pushed and saved here. So you need 3 cycles for the ISR exit. For the ISR exit, you need 3 cycles. And after that, you return officially to the main, exactly at instruction B, and you continue with the main method. One of the things that you need to be aware of is the priority. Notice that here the priority are 4, and in the ISR, the priority is more than 4. Otherwise, if it is less, if it is equal or less than 4, the interrupt service routine won't be executed. So you need to be careful of the assigned priority. Also, when we say status here, there is actually a status register associated with every instruction that is running. And we talked about this previously, if you remember. And we also, the 3 bits of the priority are registered there. So in conclusion, for the ISR overhead, the entry of the BIC24 needs 4 cycles, and the exit needs 3 cycles, and the body needs certain number of cycles, excluding the return from the interrupt. So now we can calculate the latency of any ISR. We count how many statements in the body without the return, and then we add 7 cycles to them, 4 for the entry and 3 for the exit. And since we can calculate the time, we can calculate also the frequency. So now we have what we call the FISR. This is the frequency or the number of times per second at which the interrupt service routine is triggered. Obviously, we want this frequency as low as possible. You don't want the CPU to be interrupted a lot. And you can calculate the frequency if you know the time, which we calculated here. So the TISR is the interrupt service routine triggering period, which is the reciprocal of the frequency. So for example, if an ISR is executed at 1 kilohertz, then the TISR is 1 millisecond. Now, how to calculate the interrupt service routine overhead? From these definitions, we can come up with the percentage of the CPU time taken by the by one interrupt service routine. We call it ISR percentage, which is equal to the entry cycles, or the amount of cycles for the entry, that's 4. We said for BIC24, this is 4 cycles. The exit, which is 3 cycles, and the body, which could be, depends on the interrupt service routine. The longer the code in the interrupt service routine, the more cycle you would need for the body. And then you multiply this by the FISR, the frequency at which you are entering this interrupt service routine, and you see what is the percentage of this compared to the frequency of the instruction cycle multiplied by 100. So the ISR CPU percentage, the FCY is 40 mega. This is the maximum frequency of the BIC24. So if FOSC is 80 megahertz, then the FCY is 40 megahertz. And let's say that the body is 50 instructions. So now we plug in 50 here. As you can see here, 4 plus 50 plus 3 divided by 40 mega, but we need the FISR. We need the FRSR. And we actually assume that the TISR is 10 milliseconds. If we made this assumption, then the percentage would be 0.01%. If we reduce the amount of the TISR to 1 millisecond, and then 100 microsecond, and then 10 microseconds, since we are decreasing the amount of the TISR, it means we are increasing the frequency at which we are calling this ISR. And because of this, the percentage will get higher, which is actually not wanted for interrupt service routine. You don't want this time to be very short, so the frequency of FISR is very high, which means that you are always having events that needs to be handled by the ISR. You don't want this to happen. So the golden rule here, an ISR should do its work as quickly as possible. And when an ISR is executing, it keeps other interrupt service routine of equal priority and lower from executing, as well as the main code. So we give the ISR the handle, and we say, okay, finish as quickly as you can. This way, we don't have a chaos of interrupts. Now let's see examples of the BIC24 interrupts. We will start by the change notification interrupt. We need to understand how this interrupt happens. As I said, the interrupt, if you have a certain bin, this is, for example, change notification 0 bin. Now, if you remember when we talked about the GPIO, we said that the change notification has two functions. The first one was the pull-up enable, where you can use the internal resistance. So any switch, you can plug it right away without worrying about anything. And that's what we represented by this PMOS, where the CN0 pull-up enable could be enabled equal to 1 for this bit. Now, that's the first functionality. The second functionality is the interrupt, which will be, actually, it's very closer to its name. It's a change notification interrupt. So if this bin equal to 0 followed by 1, or 1 followed by 0, this means that there is a change in the value, and it will give you this interrupt. So if there is actually an edge, whether it is rising or falling, for every edge, there is a change notification interrupt. Now, what happens here, to save the value and see the difference, you have two flip-flops. The first flip-flop will store the value, and then the second, it's like a shift register of 2 bits. So the most recent value of the bin will be stored here, and the older clock will be stored here. If there is a change between these two clock, so for this one, you had a 0 followed by 1. This is the most recent, which is this one, and this is the older clock cycle, it's 0. Now you can use an XOR gate to tell you if they are different. If they are different, you'll have 1 in the XOR output. That's if it is 0 or 1, or the opposite, 1 and 0. So now this one tells you that there is a change in the value at this bin. Now to make this value move to the output as an interrupt, a change notification interrupt, you must make sure that the enables are working. So you have a specialized or a local enable for the change notification, which is called CN0 interrupt enable. You need to set this to 1 for this value to pass in here. Now to pass it to the outside, you need to make sure that the change notification enable, interrupt enable is equal to 1, and its priority is larger than 0. Now, this enable is a global enable for all the change notification 0, and then 1, dot, 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 all the way to 23. So once you enable this, all of them will be enabled. And you can selectively choose whichever you want by selecting its local enable. Now to program the change notification interrupt, we do this by following what you see here in the code. Remember, in the main, you need to do certain configuration, and in the main, you do certain function, whatever it is. And once the event of the change notification happens, you will run the change notification interrupt service routine, or the ISR. So if you work with an interrupt driven, you will always find the main method, and you will also find another ISR indicated by this type. Usually it doesn't return anything. It's a void underscore ISR, or interrupt service routine. It's fast in this case. It could be only ISR. That's also fine. So you have an interrupt service routine, and you should know its name. If you go to the table, you will see that change notification name is underscore CN interrupt. No arguments, and you have the body. One of the most critical things, the statements that you need to worry about in all the interrupts, you need to reset its flag. Once you enter this interrupt service routine, there must be a flag for it that you need to reset. The flag for the change notification is called underscore CN interrupt flag, and you need to reset that. Now, the question is how to configure this interrupt. So at a certain bin, in this case, we choose RB13. We know that this is RB13, and it is associated with CN13. So you need to enable this interrupt body, or the ISR for the this change notification. So at the beginning, we configure RB13 as a digital input, and we know this from the GPIO lecture. We assigned its trace value to be equal to 1 to make it an input or a switch input. The BCFG, we make it equal to 1 to disable the analog. So this is a digital bin. The change notification 13 pull up enable is equal to 1. So when you connect a switch here, you don't need an external resistance. You can use the internal resistance of the PMOS, and you have the change notification 13 interrupt enable here equal to 1. So now that's the first statement, or new statement in the main code for the interrupt. We enabled the local enable. we make, or we set the local enable of this change notification. We make it equal to 1. Other than that, you assign the 3, let me call them the brothers. You assign these 3 brothers, which is what we talked about here. Flag bit, the priority bit, and the enable bit. And this is exactly what we've done here. The change notification interrupt flag is equal to 0. So at the beginning, it's resetted, and you make the priority more than 0. Here we choose 1. We could have choose 2, 3, all the way to 7. This is the change notification interrupt enable, which is the global enable for the change notification, and we make it 1. And at this point, you can write inside the while 1 loop whatever code you want. So the CPU will work normally, doing its job. And once this event happens, now you should understand what is the event that caused this interrupt service routine to be executed. It's called change notification. So it happens when at this pin, which is the RB13, which we configured as input, if the value is 0 followed by 1 or 1 followed by 0, then this will be executed. This will be executed. So here in the while loop, so just to focus on the interrupt service routine, we didn't do much. We just call a method called sleep. So what happens if you have a switch in the RB13, pushing the RB13 switch interrupt, the processor will wake up from sleeping. It will execute the ISR, then return to the instruction following the sleep, which is actually whatever is here, and then it goes back to while loop and go back to sleep again. Now the same thing happened when you release the RB13. So let's say that you have a push button, and at the push button the value was, let's say it was 1, and then once you push it goes down to 0. When you release it goes back to 1. Let's say that this is the setup for your push button. At this point you will call the interrupt service routine, which is the change notification, 2 times. One change happens from 1 to 0, and the other change happened from 0 to 1. Now this is the change notification interrupts. Luckily for this kind of interrupt, we have a bin associated for it. Actually, we have many bins. As you can see, we have CNs all over the BIC24. These are only 3 examples of them. You can look at the bin diagram of the BIC24 and you will find all of the change notification. For other interrupts, you might not have a pin associated for that interrupt. So what to do in that case? This is why we have the remappable pins. So you can remap them the way you like. Some inputs and outputs for internal module must be mapped to the RPs pin, which we call the remappable pins. As you can see, we have from RP0 all the way to RP50. So we have 16 bits that you can assign the way you like for any kind of interrupt, whether you make it input or output. Now, for the CN that we just talked about, you can see there are so many CN bins specialized for each one of them. So they are fine. But other kind of interrupt, they might not have their own bins. So we use the RPs for them. Now we will check both the input and the output. For the remappable bins, to make them inputs, you can map the following input names or the interrupt types. We have an external interrupt 1, which is int1. We have external interrupt 2, int2. we have the timer 2 external clock. The timer 3 external clock, in case you want an external clock for the timer, you have their own uh, uh, interrupt. You have the input capture. You have the UART receive, the UART clear to send. This is for the communication using the UART, and this is for the communication using the SPI. You have something for the data input, for the clock input, and for the slave select input, or the kind of the chip select. It's very close to the chip select concept. Now, how to code this? For each one of them has name. You say underscore in case of interrupt 1 and interrupt 2, because we will talk about them next. We have underscore interrupt 1 R. So you use its name and you assign it to a certain RPN. So if you want to assign them to RP7, you would say underscore interrupt 1 R is equal to 7. If you want to assign the interrupt 2 to RP9, for example, then you will assign it to 9, like this. You have another example here. In case of the UART, if you use the receiver, which is this one, underscore U1, that's the universal sender receiver, or universal receiver transmitter module. So you have the U1 receiver RX register equal to 10, and this way you assigned the RP10 for it. Notice that all of them has an input behavior. Input behavior. You are receiving something, so it inputs inside the big 24. Similarly, for interrupt 1, interrupt 2, events that happens, usually you connect them to a switch and you assign it to interrupt 1 or 2. You might ask about interrupt 0. Where is interrupt 0? Actually, interrupt 0 is very special. It has its own bin, and you can see it here. So you don't have to use removable pins for it. Now for the output case, in the output, here are some of the interrupts that could happen, and you need an output for it. Like when you transmit something in the UART, or you send a status ready to send acknowledgement. You also have the SPI. You have for the data output, for the clock output, or for the slave select output, or for the output compare. And we discussed this previously in the output compare. We said that the output compare 1, we used output compare 1, and we need an RP for it, if you remember. The way to assign this in the code, you would say underscore RP, and you choose whatever you want. Let's say you use RP3 for this output compare. You would say 3 here. So underscore RP3 are equal to 18. Now this 18 is the code for our output compare 1. And if you go back to the output compare, you will see that I said to you that just remember the code for now, and we will discuss it later. And these are the codes for each one of these interrupts. So you have this code, that's for the output compare. As an example, for the output compare, we said that we will use this code 18. And for the transmission of the UART, we have the code 3. Just to make sure you understand, for the removable pins, when you code for inputs, you use the names. You use the names. And then you assign the removable pins for them. For the outputs, you use the codes. And you assign these codes to the appropriate RP. Now let's, since now we know how to deal with the removable pins, let's move to the interrupt 0, interrupt 1, and interrupt 2, or int 0, int 1, and int 2. So we have these interrupts. It's an input interrupt source. it's configured to be edge triggered by using an associated interrupt or int x, and x is 0 or 1 or 2, edge polarity bit. So for this edge polarity bit, you can assign it to be 0 or 1. And be careful, this could be deceiving. 0 for the rising edge, and 1 is for the falling edge. Now, in a big 24, for interrupt 1 and interrupt 2, you need to assign an RP for it. You would say interrupt 1 R equal to whatever you choose. For interrupt 0, it uses a fixed pin location. And we've mentioned that. Now, let's code this kind of interrupt and see how can we do that. Again, you have a main, you have interrupt service routine with this name. Now we choose interrupt 1. We choose underscore interrupt 1, interrupt. Again, this is its flag that you need to reset. Underscore interrupt 1, interrupt flag equal to 0. Now in the main code, you need first, just so you remember, for all of kind of interrupts, you need to do the 3 brothers first, which is the interrupt flag, priority, and enable. You have the interrupt 1 flag, interrupt 1 interrupt priority, and interrupt enable, and you assign the interrupt flag and you make it 0. The priority you choose 2, it must be larger than 0, and for the interrupt enable, you enable it, you make it 1. Now there are other things that you need for each kind of interrupt. For interrupt 1, you need to assign the RP for it. We assign 12. So interrupt 1R, or the register for it, is equal to 12. And the edge polarity, we choose either falling or rising. So here we choose falling. Be careful, it could be deceiving, as I said. If when you say it's equal to 1, it means that you are falling. Now, how does the interrupt int1 work? Now, if you remember the change notification, whatever edge you have, whether it's falling or rising, it will generate an interrupt. For interrupt 1 or int1, only for the specific edge that you selected will generate an interrupt. So if you connect a switch for interrupt 1, meaning you go to the RP12, RP12 is right there. Well, it's not shown here, but you go to its location. I believe I have the whole thing here. Yes. So you go and check the RP12 for this pin, which is the 23. If you connect a switch right there, now you obviously need to configure the switch and make sure that the port RP12 is connected properly. Now, for this switch, if you press the switch, and let's say that you have this behavior, it's like press and release, only at the falling, it will generate the interrupt. At this event, it will generate the interrupt. For the rising, it won't generate anything. So an interrupt will wake up the processor at the RP12 falling edge on. Now, let's continue more examples, different kind of interrupts. One of the interrupts that we've talked about before is the timer 2 interrupt flag. Timer 2 has an interrupt, and it has its own flag. You can enable it, you set the priority for it, and so on. We discussed the timer in detail, and we reached to this equation, which is for the finding the period register, the PR2. Which is the time multiplied by instruction of the frequency of the instruction divided by the prescaler minus 1. We've talked about this before, and just to remind you, this is a quick example. Let's say in this problem, you have this big 24 with frequency of oscillation 80 megahertz. So now we know the FCY is 40 mega. But what's the value of the timer 2 control register and PR? and decimal in order to generate an interrupt every 10 milliseconds. 10 milliseconds, that's the time that we need to plug in right there, and that's the 40 meg. And we get the test each one of them. We explained this in detail later before in the timer, and we found that this is invalid. This value is valid, and this value is also valid. I choose this one. Since I choose the prescaler 64, this is going to be the control register, which is 0x0200. And this is the PR2 value. So now I can set up the timer. Now, to set up this timer, we've discussed this before. So why we are bringing this again? That's actually the last part of the question here. You are asked to write a code to use this signal to count every 10 millisecond at port RP, which is from RP0 to RP15, which is like a counter every 10 millisecond. And you are asked to write this down using the bulling technique, which is basically what we have been using before, and using the interrupts driven. And I write down this code side by side here. This is the bulling technique that we talked about before, and this is the interrupt driven. So what happens is, we configure a counter, basically the RPs, all the port from 0 to 15. We make them all output, as you can see here. We have 0x0000, and the pull-up enable and the BCFG for each one of them, we assign them appropriately. We'll go back to the GBIO lecture for detail. Now, in the main code, we call the configure counter, which is this one, and then we configure the timer. Configuring the timer is not new to you. You know how to configure it. We say timer to control register is 0x0200, and this is the PR2 that we found from the our calculation in the previous slide. And we start TMR2 from 0. You could actually take this out, since by default it will start by 0. Now, remember that we've talked, and we said this many times before, that you need to reset the flag at the beginning. And then you start the timer, you go through a while loop. If the interrupt flag is equal to 1, now you reset it again, and you start counting in the lat B. You make lat B++. This is what you do in the code. This is actually a bulling technique. You can see the while loop. If this while loop, you do something else here. Every time you enter the while loop, first you check if there is an interrupt or not. The CPU go and check. It's like it's opening the door. Are you there or not? In the game, are you there or not? So this is a bulling technique. Usually this is, or all the time actually, this is inefficient. And you should use an interrupt-driven technique. In the interrupt-driven, you can see that you have a main method, and you have also the interrupt service routine. And now the name is underscore timer to interrupt. Now, you should ask of yourself, what is the event that will call this interrupt service routine? Or what is the event that will make this interrupt service routine start executing? The event is basically the expiring of the timer 2. When the timer 2 roll over, it will start executing the interrupt service routine. So we need to set it up in the main. As you can see, same thing here is also here. And now you don't only reset the flag of timer 2. You need to do the 3 brothers. You reset the flag, you assign the priority, I choose 1 here, and the interrupt enable, I set it and make it 1. And then I start the timer, same way as we've done before. In the while loop, I do nothing. The CPU is absolutely free to do any task it wants. It doesn't do the busy waiting waste of time that you do usually in the bulling technique. Now, what happens once you started the timer? When it expires, it goes there. It will calculate the ISR, and then it go back to whatever the CPU was doing. So you started the timer, you are in the while loop, doing many tasks. the CPU's work, doing instructions. If the timer 2 expires, automatically it will interrupt, run this, and goes back to the next instruction. So what happens here? First things first, you need to clear the flag. And then after that, you add the counter. You do the job, which is adding the lat p value. Notice that whatever you were doing here, you check the flag and then do certain tasks. In the polling technique, now you don't have to check the flag anymore. Just take this part, the green part, and plug it in the interrupt service routine. And you don't need to check because this event, when the timer to roll over, automatically to go and execute the interrupt service routine. And this is very nice, very short, contained, direct to the point. Now, if I ask any of you, which one is better, the polling technique or the interrupt-driven technique? Coding-wise, there is not much of the difference. The only thing that you need to worry about is the red part here. You need to assign priority and you enable the interrupt. And obviously, the interrupt-driven is more efficient than the polling technique. Now, there is a concept that you should know when you program a microcontroller to do meaningful systems, you might have many interrupt service routines that you need to worry about. There is many tasks that you need to code, making sure that everything works together in a nice way. So one way to make things easier for you is the concept of the semaphore. The concept of semaphore. So the semaphore is we know that an interrupt checks the switch event continuously in the semaphore. When the switch event happens, the interrupts tell the main code through a shared flag. This shared flag between the main and the ISR, it's a global variable, and it's called a semaphore. And the word semaphore comes from the flags that you see for the trains. The whole idea is actually coming from they used when they have the railroad, I believe in America a long time ago. When the main code when the main code do the action, it clears this flag. So what happens is the semaphore in the program, you have certain tasks, and then you reach to the semaphore and check its value. You check the semaphore. If it is 0, just continue executing the code. Everything is normal. If it is 1, then you make it 0 first, and then do certain actions based on the system that you are working on. And either you continue the other program or jump somewhere in a certain way. Now, in the interrupt service routine, the interrupt service routine is the one responsible for setting the semaphore. To make the semaphore equal to 1, that's the job of the interrupt service routine. To understand the idea of the semaphore better, let's have a kind of a bigger problem. It's bigger than what the small codes that you've seen before. The idea is very simple. You have an input switch, and you want to toggle a lid 1, when the switch or switch 1 is pressed and released. So that's the first condition. The switch should be pressed and released. And also 15 milliseconds is elapsed to account for the debouncing delay. So now we worry also about the debouncing delay. And we do this using interrupt-driven idea with the semaphore. Assume that you are giving a frequency of oscillation 80 megahertz for the VIC-24. You are asked what is the value of timer 3 control register and the PR3 in order to generate the 15 millisecond elapsed time first. And we know this. Since we have 15 millisecond, we will program our timer 3 to do that. And it's fairly easy. We know the drill. So 80 mega, that's 40 mega, that's the FCY. I got the FCY. I know that it's 15 millisecond. I try for BRI 1, 8, 64, and 256. So this was valid when the P is equal to 8, and also the 64 is also valid. I choose the 64. So now I know that the T2 control register is 0x0200, and the pre value is 64. And also the PR3 is the value that I have here, which is this one. Actually, I round it to the top. The value here, I think it has a fraction, and I round it to 75. It doesn't matter much if you use 9374 or 9375. The difference is very, very small. So now let's write the code with the interrupt service routine and the semaphore ID. How to do this? Remember, we have a lid and we have a switch. So what we did is we have assigned lid 1 to lat B14, and we know how to configure the lid. The trace is 0, the BCFG is 1, the pull-up enable is 0, and the OBDC or the ADCB is equal to 0. Be aware of the pin numbers. You can check it from the bin diagram. And we talked about this again in the GPIO. For the switch, similar way, well, the trace is equal to 1 here because it's an input. And we also define the 3 macros. This is for checking if the switch is pressed or released. Now we define 2 states. Remember the state diagram for any switch. We are waiting for a press or waiting for a release. And we define these 2 states. We call one of them is 0 and one of them is equal to 1. We could have any other number actually. Now you define the state as usual. And here we define the semaphore. Now we call the semaphore here press and release. It's my flag. When it is 0, it means the press and release didn't happen. If it is 1, it means the press and release happened. This is my semaphore for the switch. So what's the idea? What do I want to do? Since I'm doing interrupt driven, I will have a main code followed by an interrupt service routine. Which kind of interrupt service routine? I have only a switch and a lid. So you need to understand the idea here. And the idea is every 15 millisecond, the ISR will be executed to check the status of the switch. If the switch is pressed, then released, then the semaphore will be set to 1, and it tells you that the press and release happened. So how to account for every 15 millisecond? We use timer T3 interrupt. I use timer T3 to set it up, and I set it in the main code. I configure the switch and the lid, and then I put it in a certain switch. The switch, I put it in a certain state, the wait press, the initial one, and then I set up the timer. I have timer 3 control. This is the control register. The value of the PR3, the TMR3 is equal to 0. And I set the 3 brothers, the flag, the priority, and the interrupt enable. I choose 0, 1, and 1. The priority is 1. The flag must be reset or 0. The enable is equal to 1. And then I start the timer. If the timer expires, the interrupt service routine will start executing. Now, what to do in the while loop? In the while loop, I can do any task, but before the task, I do the checking of this event. Is a press and release happen? If a press release semaphore is equal to 1, the semaphore tells me that the press and release is a proper press and release, and you can toggle the lid And also you need to make the semaphore equal to 0. And this followed what we've said here. That's the main program. You check the semaphore. If it is equal to 1, you need to make it 0. That's what we did here. Check the semaphore. You do the task that you want to do. If it is 1, then you need to set it. Now, who reset the semaphore? Now, who make the value equal to 1? The ISR. Somewhere in the ISR, there must be this state, the press and release equal to 1. Now, the interrupt service routine, just so we don't forget the first job, reset the flag, timer 3 flag, and then go through the switch statement. And remember when we had the press and release discussion before, when we talked about the GPIO, it's the same thing. It's like I copied that part and I pasted it here. So you have the switch, whatever state you have, the switch state. I call it actually state here, so it should be the same name, state. So I need to take this out actually. I set the state and I wait for a press. If there is a press, you change to the next state. If there is a release after the press, then at this point, you will raise the flag. You will raise the semaphore. You would say that press and release is equal to 1, and then change back to the press, and so on. This is the idea. So just so you understand what's going on, every 15 milliseconds, you will run here. You will run the interrupt service routine. Now, the main code will run all the time. And every once in a while, when the main code will run, usually when it checks the semaphore, nothing there. It's 0. So there is no toggle. It's always 0, 0, 0, 0. And then once the 15 millisecond passed, which is, this is actually accounting for so many machine cycles. So when this happened, the 15 millisecond already passed, you go and check if the press is pressed and released. If that's really happened, then the flag or the semaphore will be risen. I made this with a different color. This is for the semaphores, and this is for the time. So you understand it better. And that's the idea here. I believe this is one of the longest code that we have so far in the lectures. Now let's have other examples to have a full understanding of the interrupt service routine. Let's say that you have a figure with this code, and it's telling you what is the value of the counter after entering the while. That's all. It doesn't tell you anything. It just show you the main method, and it show you this routine. You should be the one to know that, oh, this is interrupt service routine. So I'm dealing with interrupt-driven methodology, and we are talking about a change notification interrupt. So we are talking about the change notification. Now what happens here is in the figure, I have RA1 and RA0 with change notification 2. I know this is change notification. This is the change notification that probably this is the one that I'm worrying about. I need to see the main code, what's written here. We configure RA0 as a digital input. So RA0 is an input. So that this is the direction. RA2 is an input. Now, RA1 is an output. Obviously, it has to be an output for this arrow to work. Now, the counter value is 0. And I make a lat A1 equal to 0. So the value here that will be given to RA0 at the beginning is actually 0. The change notification to interrupt enable is equal to 1. So now I know that I activated the local enable for the change notification for CN2. So now the interrupt is enabled here. And then I set up the three brothers, the flag, the priority, and the interrupt enable. This is actually supposed to be change notification interrupt flag without this if. Anyway, at this point, what happens is I run through for loop. Now I activated the interrupt, it's working. In the for loop, I change lat A1 value. I make it 1, followed by 0. So that's the first iteration. I make it 1, followed by 0. I use knob, so it's prolonged for a certain amount of time for 1 and also for a 0. And then I do this 10 times, from 0 all the way to 10. Notice that I is less than 10, not less than or equal. So it's actually from 0 to 9, you go inside the loop. 10, you just check and get out of the 4. And then I get stuck in the while loop doing nothing. So I know that I did this 10 times. I did that 10 times. That's only one iteration, and I did it 10 times. For each iteration, I have two change notification. I have a rising and I have a falling. So since I'm doing this 10 times and I have 2 interrupts for each iteration, the total will be 20. And for each one of these changes, so for this one, when you have a rising, you will go to the change notification interrupt and you will increase or increment the counter. And in the falling, you will do the same and you will increment the counter. The counter starts from 0. So to solve this, for each iteration of the for loop, lat 1 changes 2 times. It will generate the change notification 2 will generate 2 interrupts, and the counter will be incremented by 2. Since you have 10 iterations for the loop, you're looping 10 times, the counter will be 2 times 10, which is equal to 20. Now, we had an example where we divided the work between the main and the interrupt service routine. You need to do this. There are usually multiple ways to divide the work between the ISR and the main. And I gave you examples using semaphore and using timer 2 and timer 3. So you already have practiced this. Now, the right choice is the one that surfaces the IO event in a timely manner. And there can be more than one right choice. The golden rule here, now we are extending this. The interrupt service routine should do its work as fast as possible. Do not put long software delay into the ISR. The ISR should never wait for IO. The IO event should be trigger the ISR. It's actually the other way around. So whenever there is an IO, it should have its own ISR. But don't make an ISR, and then inside the body of the ISR, there is another IO that you need to worry about. An ISR is never called as a subroutine. Always there is an event associated with it. Now, more examples. In this example, you assume the change notification interrupt for RP13. So there is a switch connected to RP13, and you assume that it is enabled. Now here in the main method, I make it an input. The RP13 is input. And then I do the three brothers, the flag, the priority, and the interrupt for the change notification. They are activated. And I wait for this loop forever. Inside the interrupt service routine of the change notification, I have reset the flag and the change notification 13, interrupt enable, which is the private enable, I make it equal to 0. Now, did I enable it in the main? Yes, I enable it right there. So it was enabled, and you went to interrupt service routine. Once you went there, the first thing you disabled. So what will happen? The question here, how many times that the underscore cn interrupt service routine execute if this switch is pressed and released one time. So you have press, it was, let's say, here from this figure, the switch at the beginning, the value in the RP3, it was 1. When you press it, you make it 0, and then you released, you make it 1. But during this event, you went there and you disabled the interrupt of the change notification. And for that reason, you will do it one time. And this is the answer. The answer is one time on the falling edge of the input when the button is pressed, after which the change notification interrupt is disabled by the IPS. More examples. Now I change something here. The priority here, I make it 0. Because of this, you will never go to the interrupt service routine. You will call it 0 times. The priority must be larger than 0, as we said before. More examples. In this example, we have two switches, one switch connected to Nt0 and Nt1. And the problem is, give the order by which statement A, B, C, D are executed. A and B is in the body of the Nt0 ISR, and C and D in the body of Nt1. Now, in the main code, I configured the switch. I didn't write it down because I don't have space, but we configured the switch properly. And then for interrupt 0, flag priority, edge polarity, and enable, we set them up properly like this. The flag is equal to 0. The priority is 2. The edge polarity is 1, so now it's falling, and you enable it. That's for interrupt 0. For interrupt 1, it's a copy and paste. It's the same, 0, 2, 1, 1. Again, here 0, 2, and 1, and 1. Now, this switch for interrupt 0 and interrupt 1, as we said here, we configure it properly with change notification pull-up is enabled. Part of the configuration, we assigned the RP appropriate for interrupt 1. It's not written here, but we did that. Now, if you go inside the body of interrupt 0 and interrupt 1, we reset the flag in each one of them, which is good programming. And here we disabled the interrupt for the interrupt 0 inside the body, and we disabled the interrupt for interrupt 1 here. Now, what's the order? Now, you should think about priority. Now, since the priority here is 2, and this priority is 2, now you know that the assigned priority are the same. So you go to the natural priority, and you know the natural priority, you have integer 0 as having a higher natural priority more than interrupt 1. So interrupt 0 will execute first, and then interrupt 1. Why there is a competition actually between them? Because they are connected to the same switch. If you press and release, you will have a falling, and it will be fired in interrupt 0 and interrupt 1 at the same cycle. So there is a competition between them, and interrupt 0 at this case will win. So you will execute A, B, and then followed by C and D. And this is what will happen. So the answer is A, B, C, then D. Both interrupt are enabled and have the same priority. Interrupt 0 has a higher natural priority than interrupt 1, and that's why we have this order. So let's change this a little bit. We change only the polarity here. We made this rising edge. Again, this is press and release. So we have a press followed by a release. This is the press, and this is the release. Now, interrupt 0, we make it 0, and that's a rising. So here, this is the rising. And this is when interrupt 0 happened. And this is the falling. And because we didn't change it, interrupt 1 now will happen first. Since interrupt 1, there is no competition here. Interrupt 1 happened before interrupt 0, it will be served first. So now the answer is C, D, A, then B. Both interrupt are enabled. Interrupt 1 execute first because interrupt 0 is configured as a rising edge. Now, from the original code, we make another change, which is this change. The interrupt enable for interrupt 1 is equal to 0. So now we disable interrupt 1. So what will happen is we will have only these two statements, and that's the order. We have A and then B because interrupt 0 is enabled and interrupt 1 is disabled. Another change, I made the change here where I kind of, being a bad programmer, I forgot to reset the flag. I forgot to reset the flag in interrupt 1. So it's the same as the original code. The only thing here is I forgot the interrupt flag. So it's supposed to have statement A first and then B and then C. This is the order. But since I forgot to reset it, the interrupt flag, this interrupt will happen infinite amount of time. So this will be the order. You have A, B followed by C, C, C forever. Because interrupt 0 is enabled, interrupt 1 is enabled, interrupt 0 have a higher natural priority than interrupt 1, but interrupt 1 enter an infinite loop because the flag is not clipped. So at this point, we discussed the interrupt module. We gave you many examples. I hope you understand it very well. And now, next time, we will discuss the external memory. And after that, we will have few modules that we need to cover, communication modules and the conversion from digital to analog, and then we will finish this class. I'll talk to you next time.